Here's a weird thing. Based on our understanding of physics, the universe, as we know it, should not exist. In fact, all matter, the stuff that makes up you and me and basically everything you see around you, should have been destroyed not long after it was formed. As for why it wasn't, well, that's actually one of the biggest unsolved mysteries in science.
If antimatter touches matter, the two substances completely annihilate one another and convert into energy. The converse is also true. Energy can convert into matter and antimatter.
The reason we're so confident we shouldn't be here is based on our understanding of antimatter. When you hear that word, it might conjure up visions of some hypothetical mysterious substance, but that's kind of because the name, stinks. Antimatter definitely isn't hypothetical.
And this is a crucial point. When energy converts to matter, it also converts into antimatter at the same time. And not some random amount of antimatter. The amount of matter created and the amount of antimatter created are identical. This graphic drives the point home. Energy can turn into matter and antimatter, and the amount of matter and antimatter is equal.
If there's one thing antimatter is known for, it's that when a particle of it touches its exact matter counterpart, like say an electron hitting a positron, it all goes boom. It happens in a process called annihilation, and when it's over, the original matter and the antimatter particles are gone. Usually, the only things left behind are some photons of extremely energetic gamma ray light. And that's where the problems start to come in. See, as far as we can tell, the Big Bang should have created equal amounts of matter and antimatter. It was all bunched up close together in a sort of soup made of hot, dense plasma, and these particles were running into each other constantly. Annihilation was happening all the time. Now, to be fair, matter and antimatter were also forming during these early days. It happened during something called pair production. It's the reverse of annihilation. It happens when a photon with enough energy turns into two particles, one made of matter and one made of antimatter. Because it always produces equal amounts of matter and antimatter, it shouldn't have upset that 50-50 balance. So when the universe cooled and expanded and pair production dramatically slowed, that ratio should have been locked in. Annihilation should have continued to rage until there was nothing left but photons. But obviously, that is not what happened. Which is great. Instead, we have a good reason to believe that essentially all of the particles left over from the beginning of the universe are made of matter, and that almost none of them are antimatter. And that just doesn't make sense. It's not that there are secretly huge pockets of antimatter out there either. If there were, there would be a constant stream of annihilation reactions wherever those pockets touched matter, and we'd be able to see a huge number of gamma rays as a result. The only antimatter we actually see is the occasional stray particle from space, and the short-lived particles made in radioactive decays on Earth, and the handful of particles made in accelerators. Technically, it isn't 100% impossible, but it would be really hard for big chunks of antimatter to fit in with our current evidence of the structure and evolution of the universe. So the much more likely explanation is that the modern universe contains essentially no antimatter. But why?
There is simply no antimatter to be found. The prediction of equal amounts of matter and antimatter is completely falsified. When a theory is falsified this badly, something has to be changed.
The best explanation we have right now is that for some reason more matter survived those early days of chaos. Evidence suggests that for every billion antimatter particles made in the early universe, about 1,000,000,001 matter particles were made. So for every billion annihilations that made photons, one extra matter particle survived. That's just bizarre, though. Based on what we've seen, matter and antimatter should be identical. They should form the same way and should decay into other particles at the same rates. They should also be treated the same by what we consider the three fundamental forces in particle physics: the strong nuclear force that holds atoms together, the weak nuclear force that governs atomic decay, and electromagnetism. So basically, if you imagine swapping every matter particle with an antimatter particle and vice versa, your experiment should behave identically, which means there should be no reason for the imbalance that we see. Except, obviously, something had to have happened, otherwise everything would just be made of photons and we wouldn't be having this discussion. The challenge physicists have now is figuring out what caused that imbalance.
The mystery of the disappearing antimatter is a big question for modern physics. Several experiments in the recent past and the near future have studied and will continue to study this question. This is an obvious hole in our understanding of the universe, and as questions go, it's a biggie. I don't know what the answer will be, but what I do know is that scientists are doggedly following every clue, hoping to solve this difficult mystery.
Of course, scientists don't think we'll be able to solve this antimatter problem just by testing and looking at particles in the world around us. Unfortunately, that would just be too easy. Instead, it's likely that we will need to do a lot more theoretical work to answer this question. And that will probably mean coming up with a whole new framework for physics. One of the things that we might have to overturn is called the Standard Model. It is a really well-tested model that catalogs the types of particles we know and also predicts how they should interact. And even though there is a lot of evidence supporting it and it's been really good at explaining things, researchers have a few reasons to believe that there's something beyond the model too. Because among other things, it can't explain how gravity works, and gravity is definitely real and kind of a big deal. A bunch of researchers are currently trying to find something called the Grand Unified Theory that will ultimately replace the Standard Model. This theory, if we ever discover it, will be able to describe the three main forces of particle physics as if they were the same force. Scientists think that unified force would have been extremely important in the very early universe, so maybe it could tell us what happened with matter and antimatter. So maybe that unified force treats the two things differently, like the weak force does, but on a much larger scale. But the truth is, we're not really close to getting an answer.
In the 1990s, engineers poured 50 million liters of water beneath a mountain in Japan. In the last 20-some years, that water has been sitting in a giant tank, revealing all sorts of things about the subatomic world. But even after all that time, there's one thing that no one has ever seen happen in the tank, or anywhere else. A proton decaying. In other words, no one has ever conclusively seen a proton turn into other lighter particles. That might not seem like much, but it's important because physicists are pretty sure protons should decay. So the fact that no one has ever seen it happen is raising some questions. Now, when you first start looking at this research, it might seem a little weird that scientists think protons decay. After all, the main theory that explains how fundamental particles interact, called the Standard Model, says that they don't. Specifically, it says that protons can't decay because of what they're made of. Protons are made of three smaller building blocks called quarks, 2 up quarks and 1 down quark. These tiny particles can't exist by themselves, so it's not like a proton could just fall to pieces. Instead, for one to decay, those quarks would need to turn into something lighter. The problem is, up quarks are already the lightest ones out there, so they can't get any lighter. And while down quarks can turn into ups, it doesn't happen in protons. That's because together, 3 up quarks have more energy than 2 ups and a down quark do. So for a proton's down quark to change, it would need to create that extra energy from nowhere, which isn't a thing. And that means the proton's down quark stays down, and the particle stays a proton forever. GUTS, or Grand Unified Theories. These are theories that would combine the 3 forces of the Standard Model into one nice, neat superforce. Right now, there are tons of different GUTS, some more dramatic than others. But unfortunately, these ideas are hard to test against each other. That's because the Standard Model is so incredibly well verified that all viable GUTS need to be super similar to it in today's universe. These hypotheses can only diverge at much higher energies, one so high that our particle accelerators won't be accessing them anytime soon. And that's where protons come in. Many GUTS predict that the superforce shouldn't distinguish between quarks and leptons. So up quarks in a proton should occasionally decay into leptons after all. If a proton in the water decayed, the resulting leptons would give off light that would be picked up by detectors around the water. And we would finally have some answers. Of course, that hasn't happened yet. And to match that result, the project scientists have calculated that proton lifetimes must average at least 100 times longer than the simplest GUTS predicted. But there are plenty of grand unified theories still in the running, so scientists aren't out of options yet, although the lack of decays is worrying some of them.